So modes of energy transfer. We have already discussed 3 different modes of energy transfer. Modes of energy transfer between the system and the surroundings. One is heat transfer, that is Q, and work transfer, energy interactions between the system and surroundings in terms of work transfer, and with mass, that is energy transfer with mass flow. When mass enters and leaves the system, energy associated with mass flow in and out of the system. So if you have a system and surrounding, the energy transfer in and out of the between the system and surroundings in terms of Q, heat transfer mode. Work done by the system onto the surroundings, or work done onto the system by the surroundings, that is work modes. And then the energy associated with mass flow in and mass flow out of the system. Mass flow in and mass flow out. So the net transfer of a quantity, is equal to the difference between the amounts of each term, amounts of each energy transfer mode, amounts transferred in and out. So the net transfer of a quantity is equal to the difference between the amount that is transferred in and out. So how we can write energy balance? So the energy balance can be written as energy balance can be written as E in minus E out is equal to change in energy of the system, del E of system, which is equal to Q in minus Q out plus work in minus work out plus the energy associated with mass in minus energy associated with mass out. So these are the 3 modes of energy interactions between the system and the surroundings. This is in case of a flow process. This is the general expression in case of a flow process, where we can have heat transfer, work transfer, and energy in with mass in and energy in out with mass out. Okay. So in a case if a system is adiabatic, if system is an adiabatic system, the process happen in an adiabatic system may be so fast so that the system is not having enough time to exchange heat between system and surrounding. In that case, Q can be 0. Or if your system is well insulated, say for example a gas is confined in a cylinder and the cylinder is well insulated so that no heat exchange between the system and the surroundings. In that case, Q is equal to 0. So this is a closed system where there is no mass transfer across the closed system where there is no mass flow between the system and surroundings. So in case of closed system, no mass flow across boundary. In that case, the third term is 0. That is, there is no mass in and mass out, so no energy in along with the mass and no energy in along with mass out. So this term will becomes equal to 0 in that case. Okay, so E in minus E out along with the mass, which becomes equal to 0. Whereas in case of adiabatic system, there is no heat exchange between system and surrounding. In that case, Q in minus Q out becomes equal to 0. Okay, or if there is no work transfer between the system or surroundings, or the system that involves no work interactions, in that case the second term is 0. So energy balance equation can be simplified as, how we can simplify the energy balance equation for any system? Energy balance for any system, you can simplify it as del E, that is del E of system is equal to E in minus E out, that is E in minus E out. So what is change in energy of the system? It is due to change in internal energy U, kinetic and potential energies. Whereas what is this? E in minus E out? E in minus E out is the net energy transfer. It is the net energy transfer by that. This term is the net energy transfer by heat, work and mass. By heat, work and mass. Okay. So in the case of an adiabatic system, there is no Q, no heat exchange between system and surroundings. In that case, Q in minus Q out is 0. Or if the system involves no work, the second term will be 0. Or in case of that is closed system, the third term will be 0 because there is no energy in and energy out along with the mass. In that case, the system, this energy balance equation simplifies to del E of system is equal to E in minus E out. Change in the system means change in internal energy of the system, which is equal to energy in minus energy out through energy interaction modes, that is through heat transfer mode, work transfer, or through the mass transfer. So how to express energy balance in rate form? Energy balance in rate form. So we can write it as E dot in minus E dot out. That is, what is E dot in minus E dot out? It is the rate of energy transfer. Rate of energy transfer by, what are the energy interactions? By heat transfer mode, heat, work, and the energy associated in and out of the system, once mass flows in and out of the system, which is equal to dE of system, the change in energy of the system with respect to time, dt. That is rate of change in all microscopic modes of energy, that is in internal energy, kinetic energy, potential energies, etc. Okay, so this is the general expression for energy balance in rate form. Now we'll discuss about the thermodynamic cycle. Thermodynamic cycle. So consider a closed system undergoing a cycle of processes or undergoing a cycle. A closed system undergoing a cycle. Cycle or a series of processes or a series of processes or series of process where system restores its initial state. Its initial state where the initial and the final points coincide in case of a cyclic process. So we can represent it on a PV plot, pressure versus volume diagram. Okay, a closed cycle or a series of processes which in which the system is undergoing a change of state so that it restores its initial state. In a cyclic process, the net heat transfer into the system is equal to net work transfer out from the system. You know, in a cyclic process, del E of system is equal to E2 minus E1. It is equal to 0. Since the initial and the final states are identical, initial and the final states of a system, of a closed system undergoing a thermodynamic cycle are identical. The initial and the final states are identical. There is no change in internal energy of the system. Change in internal energy. There is no change in internal energy of the system, which means del U is equal to 0. So what is the mathematical statement for first law of thermodynamics? Del U of system is equal to change in internal energy of the system is equal to heat added into the system minus the work delivered by the system onto the surroundings. So it is equal to Q minus W. If you consider a system, how we derive the heat added to the system is equal to increase in change in internal energy of the system plus the work delivered by the system onto the surroundings. So Q is equal to change in internal energy of the system plus W. So what is del U? Del U is equal to Q minus W. So change in internal energy of the system is equal to Q minus W. But in case of a cyclic process, change in internal energy of the system is equal to 0 since the initial and final states are identical. Since the system returned back to its initial state and there is no change in internal energy of the entire system, even though it undergoes a transformation from state 1 to state 2 and from 2 to 1 or a series of processes, and it returns back to its initial state. In such case, change in internal energy is equal to 0. So Q is equal to W. The net heat input is equal to net work delivered out of the system. So if it is happening in case of a system where we can represent a series of processes on pressure volume diagram. System is undergoing a change of state from state 1 to state 2 and it restores back to state 1 through a process path B or through it takes up another path C. Okay, the summation of, since it takes up a cycle, it is found that there is no change in internal energy of the system. So change in internal energy of the cyclic process is equal to 0, which means del U across the path A, that is from 1 to 2, plus change in internal energy happening from 2 to 1 should be equal to 0, which is equal to del U of a cyclic process from 1 to 2 and from 2 to 1. Okay, so that is equal to 0. So in such case, how we can write? If it is series of processes, summation of all heat effects involved in the process is equal to summation of all work effects happen in the series of processes. So in a static system that is undergoing a cycle of changes, we could explain that summation of all heat effects is equal to summation of all work effects.